Hey guys, and so we are seeing the deflection of the beams, and in our previous session we just directly jump into the concept about the deflection and how can we calculate the deflection with the help of double integration method, and there is a mass moment method and also moment weight method. So in this way we have some practical understanding regarding this beam deflection, how the beam we are going to analyze with the help of the load. There is a small video lecture which I want to show you for a better understanding in very practical way. Okay, so take a look about it in this video what he is teaching, and let me come back to the understanding about this video.
Slope and deflection of beams, kind of an introduction video. I want to make this video so that you get a kind of a physical understanding of what's going on here before we get into the equations, because I think this really helps you to understand what it is we're looking for, okay? So what we're talking about today is as beams get loaded, think about our shear moment diagrams, right? And as we have beams and they get loaded, beams deflect and do different things, right? I have a super flexible metal ruler here. It's called a stays put. You know why? Because it stays put wherever you put it, it stays there. Maybe you haven't heard about Newton's first law. You know, an object at rest just stays there until somebody moves it, right? But anyway, I highly suggest to understand these properly, to look at things, you have a little metal ruler. Now you don't have to have one that's a foot long. I mean a foot long, a yard long. You can only have one that's 12 inches because they're easy to bend and kind of get to see, oh, okay, I can tell what's going here, and I can see the deflections and get a physical understanding about what it is we're looking at here, okay?
Hey, still thinking about joining the 30-day Python using AI bootcamp by AI Academy. So what if in 30 days you...
So I have drawn on the board here a couple of different beams, and just with some different connections to kind of just show you how these beams are going to deflect, okay? So we're going to look, we've got one up here that's fixed, and then pin, load in the middle, then pin and roller, load on the end, and then pin and roller with two loads on it, okay? We're going to talk about the slope and the deflection. So first I want you to just get an idea of like, what would the slope look like if this beam had that load on it? What would it look like, right? So we have this one up here. Now this one has a fixed connection on the end of it, okay? So remember, a fixed connection means that it's locked. It can't move, okay? So even if I have a fixed connection, now this is deflecting under its own weight. But look what's happening right at the wall. The beam is flat. There's zero deflection at the wall, and then it starts to slope, right? So right at the wall is none. Now what if the wall was a pin connection? What would happen? Right? It wouldn't make a very good support that way, would it? So with a pin connection, it can move all over the place, right? It'd be like putting it on your hand and letting it swivel there. But if I hold it and I make a fixed connection, now it can't move. It's going to be flat there, okay? So it's important to make that distinction. So over here, we have a fixed connection at the wall, okay? Now on this side over here, we have a pin connection, okay? So what is that beam going to look like? It's going to look something like that. So that load, as it deflects, is going to look just like that. Let me take this away and I'll sketch it. Okay, where's my blue sketchy marker here? Okay, here we go. So that deflection, the deflected beam is going to come off the wall and deflect and come up something like that. Now this is very exaggerated, okay? But we need to identify a couple of things on each one of these beams. And the couple of things we identify are this: the slope and the deflection. Because anytime we can identify, think about if I have an equation that had one of these slopes and deflection in it, if I knew what the slope and the deflection was at a point, I could maybe plug that into the equation and maybe solve for something, okay? That's exactly what we're going to do, okay? So what do we just absolutely know here, right? This beam's going to deflect like this. Well, here's what I know. At this wall over here, okay, I don't this A, we'll call this B, okay? At A, right at the wall, right? Remember, I was holding that. What is the slope? Right here, the slope, okay? Well, and I'll tell you what. Let me smear that. The slope is given by theta, okay? So it's just an angle. Okay, the slope there is, well, it's 0 degrees, right? It's completely flat right at the wall, okay? And then what else do I know? The deflection, right, the delta, right at the wall is 0, okay? The deflection is 0. And typically the deflection, we just call that y, the amount of movement up and down. So at the wall, 0. So at this point right here, I know a couple of things about that beam. Now over here,
So this is what exactly they are saying about whenever there is a flat over the beam. So in that case, that slope will be 0. Slope is nothing but it is a curve. Okay, so they just want to represent the curve, and with respect to the angle, what will be the deflection? I mean, what will be the distance from the y-axis? So that is what they are representing, their slope and the deflection of the beams. And we just go and see in detail when we are in when we having a physical classes. Okay, let me see in an upcoming sessions. Thank you.